Good afternoon, participants. Welcome back to the FTP on bio-inspired computing for data analytics. The session 12 is on deep learning based on bio-inspired computing. Respected Wilford Godfrey, sir. Welcome, sir. I request Dr. K. Anupriya, madam, to introduce the resource person.
Thank you, Sherwani. It gives me great pleasure to introduce today's resource person, Dr. Wilford Godfrey. Sir received his doctorate from IIT Guwahati. Currently, Sir is working as an assistant professor in the Department of CSE at IIT Guwahati. His research interests are computer vision and medical imaging, AI machine learning for robotics, learning analytics, mobile agents. Wilford Godfrey published more than 21 journal articles in well-reputed journals and more than 34 conference proceedings and 2 book chapters. Sir is guiding research scholars and 4 were awarded. Sir got 6 research-funded projects from various funding agencies. Sir also organized various workshops, HTTPs, conferences and webinars. Sir, we are honored by your presence, sir. Thank you. Now I request Sir to take over the session. Sir?
Yeah, thank you.
Thank you, sir.
So, good afternoon, everyone. So, it's my pleasure to give this talk. So today, we'll look at this particular topic of deep learning based on bio-inspired computing. So, basically, I'll be touching upon how this area of neural networks began from the bio-inspired inspiration, and then maybe I'll touch upon one specific problem that one can address. Um, in terms of research with respect to this area. So, neurocomputation or neural computation. So, this basically comprises of using the artificial neurons as the basic units of um, uh, computation, right? So you have architecture that is made up of these simpler units called as artificial neurons, and if you are able to do some computation or do some learning paradigm, then we call this as neural computation. So this sort of mimics the biological neuron, right? So this is one among the various methods that are used, that are said to be called as the connectionist approaches, right? So when we say connectionist approaches, what we mean is that basically, like, we have a theory called as the connectionist theory, right? So the connectionist theory basically believes that one can, one's thought process or maybe one's behavior, so or one's learning can be, or you can emulate emulate these things by using, say, neural networks, right? So that is what the connectionist theory says, right? So basically, neural networks, artificial neural networks are one connectionist approach to computation, right? So they have their basics in brain. So basically, the initial idea was to create a processing system, right? So that is what they wanted to create, and this was basically inspired by the structure and the functioning of the brain, right? So now this was the inspiration, right? So, brain is able to do very complex tasks. Somebody who has a brain able to perform complex tasks. So, effectively, like so effectively, like if we are able to mimic the structuring and functioning of the human brain, then we can. So it means that we need to create something called as an artificial uh, human brain, and that was the major idea. So basically, like creation of an artificial human brain. So how are we going to do that? I mean, so brains are basically made of several neurons, and then you mimic the architecture of the brain. So now a typical brain consists of something of the scale of 10 raised to the power 11 neurons, right? So then we create a kind of a structure that comprises of neurons, and then the idea was that we'll be able to mimic the functioning of a brain, right? So the impetus basically came from the idea that like brain is complex, it is non-linear, and it's a parallel computer, right? So basically it is able to process information parallelly, and it is able to store, or it is able to uh, decipher the nonlinearity with respect to various tasks, and it is a complex thing. So it was, the idea was to mimic the human brain, right? So what is the human brain good at? Like very specifically, I told you that it's able to perform nonlinear tasks. So we can say that it is good at pattern recognition, parallel computer. Maybe we can say it is good at perception. Then it is also highly complex, right? So maybe with respect to motor control, right? So all these three things: one is able to sense, he's able to make decisions, and he's also able to act, right? So all the, with respect to these three dimensions, any level of complexity could be tackled by a human brain. So that was the major inspiration. So the brain's inspiration was not only because of say the human brain, but we see say brain of a bat, right? So even with a brain of a bat, then we see that like they are also able to perform complex tasks. Maybe the amount of brain that a bat may be having is very small, but then still it is able to perform something called as eco location, right? So using its sonar sensors, it is able to find out the location of the flying insects, right? So it is able to find out the location of the flying insects, whether those insects, what is the size of the insects, and then what is the distance at which those insects are flying. So all of that, as the bats are moving, they are able to perform this task, and then they are able to locate these insects, and they're able to find their prey, right? So it is just not only with the human brain, but brains in general, they are very complex, and they are highly adaptive, right? So so that was the motivation for this area called as the neural computation, right? So now the other thing that it is involved with is that it encompasses distributed and parallel processing, right? So one idea is to learn, but then learn in a distributed fashion or in a parallel or compute parallelly. I mean, that is also another aspect that is inherent with respect to neural computation. One of the reasons why the area of neural networks did not take off after even after a long period was because of the lack of parallel processing machines, right? So only with the arrival of the GPU devices, the area of neural networks really took off, or the area of deep learning really took off, and it was mainly because of the lack of parallel processing devices, right? So this area of neural computation, it also allows for distributed and parallel processing along with training or learning algorithms, right? So now there are two important aspects with respect to learning. We can say one is there are two variables. We can say one is the neuronal state and neural network parameters, right? So the way how we can see is that the architecture is also important. One is the architecture, the other parameter is the weights, right? So these two aspects are very important with respect to neural computation, right? So it means that the dynamics of neural computer relies basically on these two things. One is the state, so it means the structure of the neural network, and the other thing is the neural network parameters, which are the weights or strength of the connections and the thresholds, right? So with respect to neural computation, these two things are very, very important. So when we say learning, so learning may mean one thing is to change the structure of neuron connections, or the other way to look at it is change in the weights of the interconnections, right? So these are two different ways like we can see learning with respect to a neural network, right? So now if we look at the nervous system, so it basically takes in the input, right? So it takes in the inputs, then after taking in the input, there is a comparison that happens with respect to the input, and then it produces some output. The output could be maybe some actions, or it can be some storage of the processed output in memory, right? So this is what happens with respect to typical brain. So you process the input comes from various sensory organs, and then there is some comparison that happens in the brain, and then either it is stored, or then it initiates an output through our actuators, right? So now similarly, like the neural system, it is also organized in different levels. So it means that you have different systems that are present, say in a human brain, like you have several systems that are present. Then you have different layers at which like these organization happens, and you have these neurons and synapses, like which we'll be looking at, right? So if you look at a basic biological neural network, then this biological neural network consists of importantly something called as the dendrites. Right. So these dendrites are basically tree-like structures that are made up of nerve fibers, right? And they are connected to something called as a cell body, right? So these cell bodies are the major structural part of the neuron, and these carry the nucleus, right? And now you also have something called as an axon, axon is basically the long connection that extends from the cell body to the neuron, so or the dendrite. So these are the axons, right? So these are the long connections that take something. That's so basically they are useful for transmitting the neurotransmitters, right? So neurotransmitters are some of the signals that are transmitted between the dendrites and the cell body, right? So basically, like we can see that these three things are there. Now you also have something called as a synapse, right? So what is a synapse? Now you have these dendrites, they connect to another neuron, and these interconnections are called as the synapses, right? So you may have the dendrite. So this may be an extended part of a dendrite, and this connects to, or this joins with another neuron through this synapse, right? So synapse is basically that interconnection or the junctions, and where the exchange, through which the exchange of the neurotransmitters or the action potentials happen, right? So what is being exchanged, we call this as action potential or neuro transmitters, right? So these signals are being exchanged through this junction called as the synapses, right? So now we can typically see that, like, human brain consists of something around 80 to 120 billion neurons, and a neuron is capable of receiving stimuli from thousand other neurons, right? So one single neuron, like you may have a single neuron, this may be capable of receiving inputs or signals from thousand other neurons, and what they do is they propagate these signals to other neurons, right? So now so these neural networks, or the biological neural networks, are very really very complex uh, microorgans that work in a very complex fashion. So these are the synaptic junctions, right? So now we can see that, like, through the synapse, what happens is the neuron activation, or basically the spiking or firing or triggering of the action potential happens through the synapse, right? So now, what is more important is this thing called as the synaptic plasticity. So by which, like, we have this learning that actually happens, right? So now, developing neural system is akin to a plastic brain. So basically, there is this plasticity. So now it means that the synapses get modified, right? So the junctions become more strong or more weak. So that is called as the synaptic plasticity. So it means that the synapses are not very rigid micro junctions. Rather, like, they are defined by their capability to change or modify, right? So now when the synapses change with respect to their plasticity, they become strengthened. Then we say that the learning happens, or like when they weakened, maybe we say that unlearning happens, right? So we say that the exploring the idea of synaptic plasticity is crucial for lots of learning algorithms. How this synaptic plasticity is defined, that is very crucial for many different learning algorithms, right? So just as I said, learning and adaptation, they are directly linked to this thing called as the synaptic modulation, and thus they are the very important mechanisms in a biological or a artificial neural network, right? So now if you look at the history of neural computation, so initially it started with McCulloch Pitts, and you had a initial first neural network model. So basically it had two inputs, and then you had a summation, and you had a output that is given as the function of the summation input. So now this was the initial artificial neural network model. Then this was in the year 1943, and then you had this mentioned in by somebody called as Norbert Wiener in the book called as Cybernetics. It was in 1948. Then one idea of learning that is called as Hebbian learning was proposed in the year 1949. Then there was this very popular idea called as perceptron. So perceptron was in the year 1957. Then there was this Widrow-Hoff learning rule, and then there was things called as multi-layer networks, and some of the variants of these multi-layer networks called as Hopfield networks that became popular later on. And then in 1986, say from 1943 to 1986, like we had the idea of backpropagation that was useful for training this multi-layer perceptron in a neural network, right? So I've just skipped these slides to arrive at this particular slide, where we'll be looking at a typical artificial neural network. So here, what we have is a node or a neuron, right? So we have a node or a neuron, and then so basically, like we can say that you have we earlier had a cell, so now we call it a node. Then earlier we had something called as a synapse, then now we call it weight. Earlier we had the soma, or the soma, the body, right? So now we call it the net input, right? Then we have axon, through which the output of one soma passes to the other, that you call as the output, right? So now we have these terminologies like which are akin to the biological neural network that are there in the ANN. So in ANN we have these terms, and in BNN we have these terms, right? Cell, synapse, soma, and axon. Here we have node, weight, net input, and the output. So, and you can see here that synapse, the same thing is being used here as synaptic weights, right? So the weights are called as synaptic weights. So you give the input, right? So input signals are given as x1, x2 up till xm. Then you have for each interconnection, you have a weight that corresponds to each of the input, that is given by wk1 to wkm, and then you have another input which is called as bias, right? So basically, like what we are doing is that we have a node, and so we have some inputs. So the inputs are, say, x1, x2 up till xm, and the output of this node is given by, say, if we have w1, w2 up till wn, then the output is given by sigma w I xi, I equal to 1 to n, right? So that is what is going to be the summation of all the inputs, the dot product of the inputs and the weights, right? So that is what is going to be your net input, right? Now what we have here is, so another way to look at this one is by saying that we have a weighted input, right? So it means that, say for instance, I need to make a decision on today whether I have to play or not, right? So I have to make a decision on whether I have to play or not. So the decision is based upon some variables. The variables can be what is the weather, what is the weather, and what is my temperature, right? So now, whether I have school, I mean other work or not, maybe I have a school. So based on these factors, I decide whether I need to play or not, right? Now, what happens? These variables may be x1, x2, x3, and what I do is for each of these variables, I give a weightage, right? Say, for instance, if I normalize the weights, I may have the weightages as 0.3, 0.2, and 0.5. So it means that I have given most weightage to whether I have work or not, or may I have school or not. So if I have school, definitely like my chances of playing are very less. And second important thing is what is the weather, right? So if the weather is pleasant, then I have more chances of playing. Then the third priority is given to the temperature. So some kind of weighting of the inputs is what is done by this summation, right? So now I weigh these inputs, right? Now say for instance, like the weighing of this input alone may not be sufficient. Say for instance, like if you have a simple problem, then this problem is of say drawing a uh, um, say finding out a function, right? So if the function is just based on one weight, wx, then it's going to be always going through the origin, right? So now there has to be an intercept by which I'm able to move this function from this origin to other places also. So it means I need to have an intercept term, right? So in order to have that intercept term, like we have this thing called as the bias over here, right? So we have another term that is called as the bias, right? So together with the bias and rest of the inputs, then I'm able to get the net input. And then I have something called as an activation function. So activation function can be a non-linear function, or it can be a linear function too. So based on that, like I get the output, right? So that is what is given by this particular equation, which is given by f of uk, where f of uk is equal to f of sigma j equal to 1 to m wk gxd plus bk, right? So now instead of calling this as a separate bias input, one another way is I put it along with the rest of the inputs by giving it an input 1 always and having the weight equal to the bias, right? So it becomes yet another weight, right? So this is another way, like in which I represent a generic neuron, right? So neuron then, so what is a neuron? Then it's basically a node that weighs the inputs, right? So it means that it is it just gives us the weighted sum of the inputs, right? So you get a weighted sum, and this weighted sum is put into a linear or a nonlinear function, which you call as a activation function, right? So that becomes the overall function of a single neuron, right? So there are several activation functions that are there in the literature, right? You may have a ramp function, or you may have a step function, or you may have a sigmoid function. So here, like, you have a say threshold function, or you call this as a step function, right? So if the input is greater than theta, then the output may be 0, or maybe if it is less than theta, then it may be 1 or whatever. I mean, here, if the input is greater than theta, then it is 1. If it is less than theta, then it is 0, right? So you have a step function, right? So similarly, like, you have a piecewise linear function, right? So if the input, the product of the input with some constant p is greater than 1, then you have an output which is 1. If it is less than 0, then you have an output which is 0. Between 0 and 1, then it is proportionate to the input, right? So you have this function called as a piecewise linear function. You may have this function for an activation function called as a sigmoid function. You may have a hyperbolic tangent function, and so on, right? So there are different types of activation functions, right? So now, in addition to this, we also have different architectures, basically, like how the neurons are interconnected, right? So how these neurons are interconnected, that gives way to several architectures. So here, like, we have something called as a single layer feed forward network, right? So here we see that you have the input. So it means here, basically, like, you don't have any kind of a loop, right? So you don't have the output once more coming back somewhere. So here, basically, you see that the inputs are given, and the inputs are given to a I mean, you have this interconnection with weights, and then you calculate the output. Maybe this is one layer, and then the output of this layer goes to another layer. Then you have a multi-layer feed-forward network, and so on, right? So this you call as a feed-forward network. So feed-forward network is a network where your inputs go on to produce the output, right? So go forward to produce the output. So basically, the feed-forward network does not contain any loops, right? So you have this as one kind of a network. Then you have a multi-layer feed-forward network, so where you have multiple layers, right? So basically, like, from what we were seeing earlier, so we saw a single node. So now what we see here is an array of nodes in a single layer feed-forward network. Then you have a stacked array of nodes. So you have one layer of nodes, and then you have another layer of nodes, and so on, right? So now you can also see the interconnection. So the inputs are connected to all the nodes in the next layer, and with respect to every input, there are that many number of interconnections. So basically, what you have at this layer, if you look at the interconnections over here, this is going to be, say, if there are n nodes here and m inputs, then you're going to have, say, 0 plus 1, m1 plus m plus 1 cross n matrix of weights, right? So in layer 1, you are going to have m1 plus m plus 1 into n matrix of weights, right? So similarly, like, at every layer, like, you're going to have that many number of weights based on how many number of inputs and the successive layer nodes are going to be present, right? So now if you consider like what is going to be my output, right? So how am I going to write my output? So how do I write the output? So the output then is going to be equal to say this, the net input over here is going to be equal to W1x. So if you consider this as the matrix and this as the vector of inputs, this is denoted as x and this is denoted as W1. Then we have W1x as the net input at this layer. And then over here you're having an activation function that is given by say F1, right? So now this becomes the output from this layer, right? Now what do you do? Here you have another matrix, right? So this may be given by W2. So now you multiply this one by W2, right? So now what is this output? This is going to be say F2 of W2 into F1 of W1x, right? So this is going to be the output from here, right? Now, what's the output from here? Here there is going to be another weight that is going to be W3, and this is going to be the output. So you're going to have W3 into F2 of function. This is what is going to give you the output, right? So we have this kind of a function, right? So the output can be written as this particular function. Now there is another network like which earlier we saw in the history of neural networks. We saw that there is a network called as Hopfield network. So here we see that this is not a feed-forward network. So it means that this is this, you can see that this has cycles, right? So it means the output from here once more goes in as input, right? So this has a name which we call as the recurrent neural networks, or like where like you have this kind of interconnection. They are called in general as recurrent neural networks. And in the earlier times, like one of the recurrent neural networks are called as the Hopfield neural networks, right? So now we have this as one of the representative architecture of a recurrent neural network, right? So now, if you look at the learning paradigms, then we see that we have supervised learning, unsupervised learning, and reinforcement learning. And with respect to neural network, also like you can perform any of these different learning paradigms, right? So you can perform supervised learning or unsupervised learning, or you can perform the reinforcement learning, right? So if you look at the excuse me. So if you look at the supervised learning, so what you have is that you have the desired output that is also given in as and then there is a comparison that happens with respect to the desired in output and the uh, output that is computed, right? So you have something called as yj of t, that is called as the computed output, and dj of t, that is called as the desired output. And now the difference between these two is called as the error, right? So now this error may be used as use it as feedback, so as to change the weights, right? So now with respect to the weights, right? So basically, like in any learning algorithm, you are basically interested in finding out uh, uh, the weights, right? So I told you that in a learning algorithm, two things are very important. One is the architecture, and the second is the parameter, right? So the parameters are the weights, right? So now given given that like you are required to learn something, then you are basically interested in finding out the optimal weights, right? So if you consider, if you plot the space of the weight, right? Say for instance, you have a variable a, right? A denotes the weight, right? So a can have a range from 0 up till say 100, right? So it means that a will range from 0 up till 100, right? Now you can plot like what is going to be the error at various values of this a, right? So it means that you may have error, less error over here, and the minimal error over here, right? So this is going to be the minimal error, right? And here like it's not the global minimum. So this the place where it's minimum across the entire errors, entire weight space. This is called as the global minimum, and this is called as the local minimum, right? So you may have a error space like this, right? So it means this is the global minimum and these are all the local minimums, right? So if you kept the weight as this one, you may get local minimum, not the global minimum, right? So basically like you can have a plot between error and the various weights with respect to this supervised learning setup, right? So basically it also means that like you have this desired output already available to you. It means that there is a supervisor or a teacher who is available to you, who will teach you like how you should or like what should be the optimal weight, right? So he will not say like how you should change weights, right? So this teacher, this desired output value will not say you like how you should change weight. Rather, like he will say what may be the optimal or correct output, right? So that is what he may say, right? What he says is this may be the correct output is what he says, but then like there has to be something called as a weight change that needs to happen in order to change the weights, right? So this is with respect to a supervised learning setup. In an unsupervised learning setup, like there is no supervisor who is present, it means there is no error value, because I give the input and I get the output, but I don't have any d values. It means that I cannot compute my error, right? So unsupervised setting is a place where you do not have any supervisor or a teacher and there is no error value, and only based on the stimuli and the learning has to happen only based on the input stimuli that the network receives, right? So it means there are no targets for the outputs, right? And the network themselves discover the patterns or the correlations and how to categorize the input, right? So basically this is a self organization process. So in the earlier days itself there were several self organizing neural networks like SOM, self organizing maps and so on, right? So which basically worked on this unsupervised learning setting, right? Then we also have this thing called as reinforcement learning, which is based on um, some interaction from the environment, right? So it means basically like there is no explicit supervisor. So supervisor in terms of the global or in terms of desired output may not be there, but then like this is best suitable for problems which have which go through multiple states, right? So at the end of this problem, eventually like you get to have a result, and based on this result, which may be a positive result or a negative result, the entire network learns, right? So the network that is responsible to change the machine to over to various states that learns based on the end result, right? So that you call as the reinforcement learning setup. So So basically, this is what you call as the reward or the penalty, right? So it means there is no supervisor. Basically, like we tend to learn in this fashion, right? So maybe like we experiment and we get some penalty or reward, and then like we know whether our experiment went well or like we have to change something, right? So that you call as the reinforcement learning. So now perceptron like was one of the major breakthroughs in the area of artificial neural networks. So of course, like still like the area grew like to a larger extent even after that. So now this is a very important slide. So here I'll just pause for a minute. So if you want to ask me something, you can just ask. We'll go further. Okay. So now there are various learning tools. So basically, like we looked at so far, we looked at the structure of neural network. So we looked at initially we looked at a biological neuron. Then we looked at the structure of a artificial neural network. Then we saw that weight change or weight adaptation is learning, right? So now the question is how to change weights, right? So one large perspective is called as the error correction learning, right? So basically like this delta rule and backpropagation are basically some variation of this error correction learning, right? So in error correction learning, basically you have this supervised this comes under this supervised learning paradigm. And here what you have is that you have input signal, and you have a comparator, and you have a target output, right? And based on the difference between the output, the computed output, and the target output, you calculate the error, right? So error is basically the difference between the computed output and the desired output, right? Based on this, what happens is the weight between the hidden layer and the output layer are changed, right? So based on this, the weight between the hidden layer and the output layer are changed. So this you call as a error correcting learning, right? So to what level this weight is to be changed? So basically, like W is to be added with, say, some delta W, right? Now, what is this delta W? How do you calculate this delta W, right? So that is where then this delta rule and the backpropagation rule varies, right? Now, with respect to the error correcting learning, so the delta W is given by uh, eta into E of E into X of, right? So basically, E is the error, X is the input, and the product of the error and the input multiplied by some constant eta, or maybe you can call it a learning parameter. So based on this, like your delta W will change, right? So that is what, this is what is given by this error correcting learning. So error correcting learning basically gives you this particular relation, right? So this gives the relation between the change in weight and the input. So that is proportional to the error and the product of error and eta and the input, right? So that is what you have. Similarly, there are many other types of learning also. One another thing is called as memory based learning, or you have something called as Boltzmann learning, or Boltzmann machines, you call it, right? So there are different other types of learning. One another important type of learning is called as this Hebbian learning, right? So as you see here, like this Hebbian learning is associated with this unsupervised learning, and this is also one of the very oldest and simplest learning rules that has been proposed by scientist named Donald Hebb, right? So now basically, like his idea is based on this concept of two interconnected neurons, right? So you have these two neurons that are interconnected with each other, and they are interconnected over synapse, right? So this is the synaptic junction, right? So there are two neurons that are interconnected, right? So now when both of these are fired at the same time, right? If both of these um, mm, fired at the same time, so it means there is this synchronous firing of these two neurons, then it implies that the synaptic weight is to be increased, right? So this learning rule basically says that if both these neurons fire at the same time, you increase the synaptic weights, and now if one is fired and the other is not fired, or like if they are not fired at the same time, then what happens is the synaptic weight has to be decreased, right? So this kind of a synapse is called as a Hebbian synapse, right? So this is based on the idea that the weight has to increase. So basically, you have a neural network, right? The weight has to increase if these two nodes are firing at the same time. If these two nodes simultaneously do not fire, then the weight has to be decreased, right? So that is called as the Hebbian learning, right? Say, for instance, you have this node that is given as, say, X, and this is given as Y, then we give the delta W as equal to eta into um, uh, Y into X, right? So this is what is going to be the change in weight. So where X is the presynaptic signal and Y is going to be the post synaptic signal, and eta is the rate of learning, right? So basically in Hebbian learning, there is this concept of excitation and inhibition, right? If two neurons fire at the same time, then the synaptic junction is excited, right? If two neurons do not fire at the same time, the presynaptic signal is maybe inhibited by the postsynaptic signal, right? So whoever has the higher whoever is excited will inhibit the other one. Say if X and Y are there, Y is excited but X is not excited, so Y will inhibit X, right? So that is the idea with respect to Hebbian learning, right? So basically, like here you have an unsupervised learning. We will see this a little later, right? So so here you have this associative learning, which is called as the Hebbian learning, right? So just we keep these ideas into our mind. So these two ideas, one is the error correcting multilayer perceptron, and basically with the supervised learning, and Hebbian learning that goes with unsupervised learning, right? So mm, now, we know, we already have told repeatedly that our problem is basically how are we going to adjust the weights, right? So we have an input pattern, we have an output pattern in the supervised setting, and we have some net input by multiplying the weights, and which gives an output which is equal to 0, but our desired output is say 1. Then what we are going to do is we are going to adjust the weight so that this situation is remedied, and our current output matches our target output pattern of 1, right? So that is basically the learning problem that is done. So now how is it done with respect to perceptron? With respect to perceptron, or say with respect to error correcting learning, so I told you that it is going to be equal to eta into E into X. E is the error, X is the input, and eta is the learning rate. So basically we can see here, so weight change is proportional to some small constant into target activation minus spontaneous output activation. This gives you the error into the input activation. So that is going to be your weight change, right? So so here we have the function, right? So now if you write it as a equation, then you have this specific equation, right? So um, um, now perceptron was a very important milestone in the area of neural network. So, and it was one of the first major breakthroughs in the idea of connectionism, right? Now, if you look at the perceptron, like it had a few drawbacks. One was that like it was at that time it was able to represent only linear separable problems. So linear separability was a major issue. So basically, like if you with respect to perceptron, they were able to model only linear discriminators, and so it means that if there are two classes, then you could only have a linear decision boundary. And if these two classes were not linearly separable like this, then you cannot separate using a linear decision boundary, but you need a non-linear decision boundary, right? So at that time, perceptron was not able to solve this, and this was caught by one typical problem called as the XOR problem, right? So then by later on it was found that by adding more layers, right? So instead of only having a single layer, you add more layers, and you could solve this linearly, non-linear, separable problem. So it means that by adding more layers, you could have non-linear discriminants, right? So that was later proposed, which was multi-layer perceptron. And we saw that, like, with respect to multi-layer perceptron, you have the inputs that are connected to every, you have interconnections to every node in the hidden layer. So you had multiple hidden layers, right? So now, uh, with respect to multi-layer perceptron, as we saw earlier, like, we could represent the weights by matrix, and maybe, like, we could have this. We have already seen this. So now, once more the problem comes back, which is that, like, how am I going to train the weights with respect to a multi-layer perceptron? So one of the algorithms that was proposed was the backpropagation algorithm. So of course it works with feed-forward networks. So it means that the network will not have any cycle, but then the idea of learning is called as backpropagation. So it means that the network will operate in this fashion, feed-forward fashion. But in order to learn the weights, what you do is we backpropagate the errors, right? So as to change the weights, right? So initially, like, you keep the weights as random, right? So activation with respect to backpropagation is that, like, you should have a differentiable activation function, right? So maybe typically you have a logistic activation function. So you have this backpropagation algorithm. So how is the weight change? Its weight change is same as some small constant, error, and input activation. The idea is the same as the delta rule, and that we saw that with respect to the learning that we do with respect to um, the error correction learning. So all of this is based on error correction learning, right? So we have a bit of a variation with respect to how the errors are modified with respect to an output layer, or like with respect to the hidden layers, right? So otherwise it's the same. Now they found that, like, it takes a long time to learn, right? So backpropagation takes a long time to learn. So they added something called as a momentum term, right? So by which, like, the optimal weights could be obtained faster, right? So so that you call as the uh, momentum term, right? So now one of the killer application with respect to backpropagation is called as net talk, right? So net talk is basically pronouncing the English text, right? So this had a very high accuracy. Say after 50 epochs, they were able to achieve 95% accuracy, and it was a database of around 1024 words. So at that time, like, it was the killer app. So backpropagation weight change happens either through batch learning or something called as online learning. So when have you to change weights? Like, so that is what is being told by these two ideas called as batch learning and the online learning, right? So yeah, so you have with respect to the net talk app, you have when to change weights, earlier what we saw was how to change weights. How to change weights? I will change using the error correction algorithm. One of the error correction algorithm is backpropagation. Now, when should I change the weights, right? Now, I have in the database consisting of 1 to 1024 words. Now, for one input, I have a corresponding output, and then I change the weights. Or for I will give all the inputs, then I will give all the outputs, accumulate the error, I will sum the error, and then I will change the weights, right? So I give one input, output, then error, change weights, or I'll give all inputs, all outputs, calculate the sum of the errors, and then change weights, right? So that is these two different types of learning. One is called as batch learning, one is called as supervised learning. So now, still, like even after adding this momentum term and so on, like we see that the learning is still slow, and it forgets, right? So it means that new learning rapidly overrides the old representations, and it means it is very hard to keep the networks update with new information, right? So it means that it is quite different from a human memory. But then the positive points are that it has few parameters, and it could be applied on a wide range of data. So now it means that error correcting learning. So this is what we have been seeing, right? So it has been very important in the brief history of connectionism, right? But it has limited plausibility as a psychological model of learning and memory, right? So now what we see here is then the area of deep learning, right? So earlier we saw NetTalk, right? So that itself was providing good output with multiple layers and ANN. So now deep learning was providing breakthrough results in speech recognition and various applications today, like we see today, that deep learning is able to produce wonderful outputs. So basically, like we can see what is deep learning, we can say it means neural network with several layers of nodes, and we see that these layers basically perform feature identification and processing in a series of stages, right? So in the earlier cases, what we saw was that yes, layers were present, but then more visualization and the capabilities of the layers could be highly seen with deep learning, right? So this is the question. Multi-layer neural networks have been around for several years. What is actually new, right? So what is new is that the learning algorithms have changed, right? So earlier we had good algorithms for learning the weights in networks with one hidden layer. What's new is that the algorithms for training many later networks have changed, right? So um, now what we see here, I'll just give a run through with. So what happens is in this set of slides is that you need to get the optimal weights. So what happens is at every step, you have the input, you have the weights, then you calculate the net sum and maybe a function of the net sum, right? Then you check like where it is, and then you keep training you keep changing the weights, right? So every time you change the weights, so it means the weights are being continually changed, right? So now every time you change, what happens is that this decision boundary, it keeps changing, right? So as the weights are being adjusted, the decision boundary to separate these two classes, it keeps on changing, right? So so that is what happens, right? So you have a nonlinear decision boundary, and initially, like you started with a naive decision boundary, right? So as the weights were updated, this decision boundary keeps on changing, and what we see here is that typical, I mean, the traditional learning algorithms, they required thousands and thousands of tiny adjustments on these decision boundaries in order to arrive at the optimal result, right? So there is a requirement to better these. There was a requirement to better these learning algorithms. So it means we had several algorithms in order to do that. And say for instance here, like one another thing with respect to deep learning. So one is that we needed to have better learning algorithms, and the other thing is that deep learning also provided us the idea of detecting and visualizing the features, right? So say for instance, you have this MNIST data set and you had this array of input. So basically it's the numbers, and in the hidden layers, like say for instance, this layer, what we could see is we could see some of the elementary features of the input. So the elementary features of the input basically means that maybe it can be the vertical lines, or maybe in the later layers you may find some of the horizontal lines, something like this, right? So either the vertical lines or the horizontal lines, or in the later layers if there are some circles and so on, right? So the sophisticated patterns of the inputs could also be represented by the intermediate layers in a deep learning network, right? So that is one another idea with respect to deep learning, right? So that is one another reason like why we should have multiple layers, right? So they also say that brain too works in the same fashion, right? So brain also has multiple layers, and it works by having multiple layers. So now I'm just running through this part. So this is another thing that I'll just say. So one way to train the multi-layer neural networks, apart from the age-old backpropagation, was this kind of a training, right? So instead of training by backpropagating, what we do is like we try to get the optimal weights layer by layer, right? So this kind of an idea was also used with respect to deep learning, and this way we train the multi-layer neural networks, right? So this way of training the neural networks, but then this always depends upon whatever is the error function. So it means that instead of training the entire changing the weights across the entire network, what I do is I keep training the weights across these two layers, or this particular layer, and check like what is going to be my output, right? So this happens with respect to an architecture called as an autoencoder, right? So here an autoencoder is trained with an absolutely standard weight adjustment algorithm to reproduce the inputs, right? So this happens with respect to autoencoder. So this way, like there were several changes, and we had many types of deep learning algorithms, right? So now what we come here is that does the brain also do deep learning, right? So now we saw that we wanted to mimic the brain, right? In order to mimic the brain, like we came up with neural networks. Then these neural networks slowly moved into deep learning. And now is the brain, or this area of deep learning, is it really mimicking the brain? Look at this, that there is an architectural similarity with respect to the brain, and or like with respect to the CNN, like which is one of the deep learning algorithms, and the visual cortex, right? So there is some architectural similarity with respect to CNN and the visual cortex, right? So but then like So basically, like what we are doing, trying to do is there any commonality between ANN and BNN? BNN means biologically neural network, and ANN means artificial neural network, right? So now the similarity is this thing that in CNN, like which is a convolutional neural network, basically you have a sequence of layers, right? So not the neurons as in an artificial neural network, but maybe you have other layers like convolutional layers and maybe max pooling and so on. So different types of layers are present. So, but then there are layers which are present, right? So this way it is similar to this area called as the visual cortex, right? So the layering of the CNNs is quite similar to the visual cortex. So what we can say is that architecturally, yes, they are similar, right? So it means that architecturally our deep learning algorithms are representing the biological uh, um, organs, right? But then, like, the other question is that is there any representational similarity, right? So is there any representational similarity of the CNNs and the biological neural networks, right? So in order to check this, like just now we saw, if you look at the first layer, maybe in a, deep network architecture, then what you're able to see is that you're able to see these horizontal lines, these diagonal lines, maybe the vertical lines, and so on, right? So these basic features are able to be seen with respect to in a say in a CNN network, maybe with respect to say MNIST dataset uh, training, right? So what it means that we are able to visualize the weights, right? When you visualize the weights, you are able to visualize the features, right? On visualization of the weights, we are able to visualize the elementary features. And as you go up, you may be able to look at circles and maybe some sophisticated patterns and so on, right? So so it means that in CNN we are able to see that the layers, the initial layers represent some elementary features, and the later layers represent some sophisticated features. Now, if you look at the now the question is like, is it the same with respect to a biological neural network, right? So what happened was that what they did was they took the researchers, they took a cat and they put electrodes onto certain parts of the brain of the cat, and they gave some different patterns as input on the screen, and they checked which part of the brain gets excited, right? So they basically checked which part of the brain gets excited on giving different inputs, and they tried to analyze like how and if it is it uniform and so on. So maybe whenever they gave these say whenever they gave a pattern of this form, they found that the same part in the cat's brain got excited, right? Maybe so it means that cat also is able to have some representational similarity of the inputs, right? So it means that if two inputs are same, similar, then the cats are able to recognize it, right? So it means that our CNN is able to mimic the or CNN as a deep learning algorithm is able to have a similar architectural similarity, as well as it is able to have a same representational similarity, right? But the next question is basically that whether the brain does back propagation is the next question, right? So now how are the deep neural networks trained, right? So the deep neural networks are to be trained, or basically trained in a end-to-end manner, right? So we use backpropagation. So in backpropagation, like I give the input, I find out the output, then I propagate the error back, and then I check, I use this error, and then I change my weight. Then I use this error to change this weight. I use this error to change this weight, right? So now I propagate this right from the back to the input layer, right? So I keep doing this, and then I change the weights, right? So it means that the deep learning neural network uses an end-to-end training, and which uses this backpropagation, right? So now, is this training, so with respect to training, right? So with respect to training, are the ANN and BNN similar? Right, so that is a question that is being asked, right? So, with respect to training, is the ANN and BNN similar? And we find that now, with respect to our normal backpropagation, so what we do, we propagate the input, then over here, like what is the term that we use? We compute something called as a loss function, right? So after computing the loss function, then use the derivative of the loss function with respect to the weights, and then you incrementally update the weights in the intermediate layers to find. So it means the weights are updated in a non-local manner, right? So it is non-local. What do you mean by this? It means that if I have to update the weights between these two layers, then I need not only know what is the output from this layer or this layer, but I need to know the output from this layer, right? And then transmit, and this thing is transmitted over here to make the change over here. So it means that the update rule is non-local, right? So what we see here is that the update rule that we use in a backpropagation network is non-local, right? Now we try to recall what we learned with respect to the Hebbian learning. In Hebbian learning, what we learned was that if there are two cells, one is called as a presynaptic cell, and this is called as a postsynaptic cell, and this is the synapse between this cell and this cell, right? Then what we see here, the update rule is given by this particular equation, right? So if we are trying to learn the strength of this synapse, which is delta W mu I, we can use this. We can use the outputs from these two cells only in order to perform in order to find out the strength of this synapse, right? This synapse strength is found out only using the information that is available within I mu and II, right? I can use any complicated function, but then the input has to be only between I mu and II, right? So that is the information that is available to cell mu and the information that is available to cell I, right? So now what we see here is that this is the major difference between uh, biological uh, and the um, artificial neural network learning that is happening today, right? So in today's artificial neural networks, what we do is we basically use non-local rules, but then in real world we see in the biological world we see that the update rule is local, right? Another important factor is this thing called as the supervised backpropagation learning versus biological learning, right? So now, in order to most of the algorithms, say in deep learning algorithms, 80% are supervised, right, or even more are supervised, right? Now, since they are supervised, if you compare with how learning happens with respect to say teaching children, it's not that like you always use these flashcards and the children learn the difference between cat, or they try to find out the similarity between different cats that are given to you. You don't give all possible flashcards and then ask the children to learn what is meant by a cat, right? So most of these child psychologists also, they believe that children don't learn by flashcards, right? Small children, they don't learn only by flashcards, but rather how they learn is they are exposed to high visual stimulus, and the visual world, and then because of that maturity they are able to learn, and this is highly unsupervised, right? So we see that on the other hand, most of the algorithms that we use are supervised learning algorithms, right? So it means that there is a difference between how we learn and how we think that we should learn, right? So currently, like how algorithms learn, or like how the algorithms have been devised, and how we think that like they should be devised. So the important question then is that given this kind of unsupervised aspect of learning and locality, so it means there are two things which we have talked. One is the local aspect, and the other thing is the unsupervised aspect, right? So given that like we see that learning has to be unsupervised, or we should tend for learning to be unsupervised, and we have basically local synaptic plasticity rules, can we have a learning algorithm that is able to perform good generalization by incorporating these two ideas, right? So that is what we see here, right? So we have this learning algorithm. Let us assume that we have a simple neural network that has one set of weights and one input layer and a hidden layer, right? So this weight is going to be represented by a weight matrix, right? So now we are going to learn this weight matrix, right? So now we have these equations that have been given here. So now, in order to solve in order to here we are going to present the inputs. So if you look at this equation, it has three terms: 1, 2, and 3. So first, the first term is the input, right? So you have the if you take a MNIST data set and you convert that into a vector, then you have a vector of inputs. So you have this as the input vector, right? Then you have the the hidden input, so which is given by h mu, right? So then we also have the second input. So the second input is given as the product of W inhibition in into sum of R of HV, right? So this is going to be the this is going to be the input to the um, thing. So basically, what it means that this particular function, what it means is that, so I told you about the exciting and inhibition that happens with respect to Hebbian learning, right? So in Hebbian learning, you have these two cells, right? So one is one neuron, the other is other neuron. You have the synapse that is between these two neurons. And now, if both are excited at the same time, then there is a positive value for the synapse. If both are not excited at the same time, then whoever is excited more is going to inhibit the other one, right? So that is what happens with respect to this particular function, right? So basically, you have a differential equation there. So it sort of signifies the competition that exists between the hidden units, right? So now when the data is presented, some neurons are more excited than the other, and then what they do is they are going to suppress the others, right? So that is what is given by this W inhibition, right? So so now we have this particular function, and you have this input that is given as Vi. Vi is the original input, and Vi into W mu I is what is given by this I mu, right? So I mu is going to be equal to W mu I into Vi. So you have this I mu, and then you have a differential term. So this is basically this represents this Hebbian learning term, and then you have this H mu term, right? So these three terms together give you a differential equation, and you have to solve this particular differential equation in order to obtain like what should be the value of this delta mu I, right? So now if when you solve this differential equation, what you see is that since this is a differential equation, you may have a range of values that these terms can take. So maybe like they keep changing, right? So until they become steady, right? So you have these hidden layer inputs that vary in these different fashions, right? So they vary over a period in time, and then they become steady, right? So it means H3 is it takes a positive value, and as it becomes steady, maybe some other term like they get close to zero value, maybe some get negative values, and so on, right? So similarly, like you also see that this change in weight is given by earlier we have seen that delta W is going to be equal to eta into H into V, right? So that is what we saw. Like if H and V are two different cells, then the delta W is given by eta into H into V. So what we see here is instead of H, what we have is a function of H, which is given by g of H, and the function is given by this particular diagram, right? So this diagram shows what kind of function that it is, right? So if the value of input is more than this H star, then you are having a positive value. If it is less than H star, then you have a negative value. It's similar to a kind of a step function, right? So now like you have together these equations make up the idea of Hebbian learning, right? So there are two aspects to this Hebbian learning. One is that this uses only these two layers, right? So none of the other layers are being used. Only these two layers are used to compute the change in weights and the optimal weights. And the second thing is that there is no output at all, right? So there is no output that is present in order to train these in these two the weights between these two layers, right? So there is no output. There is local input that is given in order to change the weights, right? So now what happens is like this is only with respect to two layers. Now when you stack this algorithm across multiple layers, then what we have is the stacking of these layers, and you can stack it across an entire network, right? So you can have a neural network, and then you can stack this kind of a learning across all this entire set of sequence of layers, and then like you can perform training, right? So this is the result of training that is performed with respect to MNIST dataset. So in MNIST dataset, like basically you had these numbers and then you train. What we see here is very interesting. So this is using the traditional, say, backpropagation training, and this is the output with respect to biological training. So now, if you look at the result with respect to backpropagation training, so this is the result. It means the error becomes zero very quickly, right? So with respect to backpropagation training, this has the best result, right? So this has the best result, right? So backpropagation training is the best am I audible? Hello?
Yes, sir, you're
Yes,
audible.
sir. Audible, sir.
Yeah. So the backpropagation training is the best of all these results. But if it comes to say biological training, so using the algorithm that we just presented, if you are looking at the training, so it is still better, but it is not so good as backpropagation training. But if you look at the testing, right? So biological and backpropagation testing, biological testing still performs better than the backpropagation testing, right? So it means, see, the important thing to note here is that there is no supervised data, right? So backpropagation algorithm used supervised data, but biological training algorithm did not use supervised data. Sorry, biological testing algorithm did not use any supervised data, right? Biological testing algorithm did not use any supervised data. Now, backpropagation training algorithm used supervised data, but still it is not able to perform so well as, sorry, I'm mixing. So right now we are comparing only the testing algorithms, okay? So I'll just write the testing algorithms, biological testing and backpropagation testing. So here we have biological, this is backpropagation testing, and here we have biological testing, right? So as time goes on, which is performing better? It is the biological testing which is performing better, right? Backpropagation testing is this one, it is still not performing so good, even though you have provided it with supervised data, right? So this is a very significant thing, that as we make the algorithms that are closer to the biological network, we are able to get results that are far better, right? So this is just a example of like how the biological algorithms work. And so the conclusion is that, like, we see with respect to this set of slides, what we see is that the generalizing performance of the biologically plausible neural network is closer to that of the neural network trained end to end. So it means that these two are quite closer to each other, right? And of course, like, the weight of the intermediate layers do not have any information about the task. With respect to our biological training, they did not have any information about the task that they need to solve eventually, right? But still they produce a general and true information of the data, right? So representation of the data. So I just want to conclude by saying that still there is lots of research that is going on in this direction to exactly mimic the bio-inspired or exactly mimic the bio-inspirations. And I mean, still, like, we are still a far distance away from really doing it. And as it is shown in this particular example, if we are able to really mimic the biological algorithms, then maybe, like, more things are yet to come. With that note, like, I would like to close, and if you want to ask anything, like, you can ask. Thank you.
Thank you, sir. Participants, any questions from your side? Okay, sir. Thank you, sir. Thank you so much for your talk. And thank you, sir.
Okay, thank you.
Participants, this is the end of today's session. And the feedback link and attendance link will be given in the WhatsApp group, even in the chat box also. Please fill that. And thank you so much.